equation, please.
Thank you. I'd like to thank the organizers and everybody for inviting me and giving me a lovely, well, just thinking about it, I've done nearly a year here at Christ. Today I'm going to talk about something that's pretty close to home, and Graham's already alluded to it, the Pantograph equation, which you see up there. It's a frustratingly simple-looking creature. It's this term here, this alpha. That's a constant, but it wouldn't be very interesting if it were 0 or 1, for example. So it's some constant. Various papers I've looked at it for complex, real. The important part is whether or not it's an advanced equation or retarded. So if the modulus is less than 1, between 1 and 0, it's called a retarded equation. So if x were time, which it never is in my stuff, but then it would be sort of the present state is dependent on a past state. And in some of the most interesting ones, the modulus of alpha is greater than 1. So that sort of future depends, or past depends on the future, I guess. But x here is almost always a spatial coordinate. Now, this equation's got a long history. And I've got to say, I'm probably the first person at an IMI, or maybe even some industrial mass conference, that ever bring up number theory. Industrial number theory, what's that? I don't know. I'm not going to talk about it, but I will talk a little bit about that partition problem. You'll find that this equation, as simple as it is, has got so much rich structure that it has occupied mathematicians for decades. A lot of first-rate people have worked on it, and I bring it to this conference because it lay dormant in here on these occasional applications, and it absolutely exploded in a math and industry problem with John Ockenden and Leslie Fox and Alan Taylor. They worked on this problem. They derived this equation quite independently of whatever was going on before, and a huge surge in interest happened. People like Bryce McLeod and Toto Kato and others all worked heavily on the analysis of this equation, writing 40-page papers for the Transaction of the American Math Society and things like that. So, needless to say, as simple as it looks, there's a lot going on here. And I just want to point out to kind of answer a little bit about one of Graham's questions. What does a problem in industry offer a person as a mathematician? Are you creating any new maths? What's the interface? And my answer is this is a great example because you see what some of the applications are. So you've got Pantograph here. Can anyone read that?
Okay.
Anyway, you got applications. You got the Milky Way, right? You got gambling. Now everyone likes that. You got the electric train. You've got cell growth, which Graham is, and Alistair Paul have got, and some other applications as well. What about on the other side? This is applications. Okay, what about on the other side of this? Maths. What's it done for mathematicians? You know? And I'll tell you what it's done. It's solved or helped solve, and I'll take you through one very briefly, problems in number theory, though it's unexpected connection, problems in theta functions, repackaged. It's also theory of course, functional differential equations and ODEs, and it's also impacted probability. Those are the ones I thought of 10 minutes ago. Just from papers I've read where this equation has popped up and had something to add to those fields of more pure maths. That really can't be read, can it? Okay. All right. Okay, so I've outlined some of that here in this, queuing theory. I don't know that application very well, so I won't say anything about that. But the first thing I'm going to talk about, I'm going to jump all the way over to theta functions, because I've been bothering poor Professor Kim Hong-Oh for I don't know how many visits saying, I think this is all tied up with theta functions. And Hong very patiently sat through my explanations and sort of politely said, yeah, maybe. And then I found the connection, but I also found that maybe I was a bit late on that one. 1931, but it's essentially sitting there in a different form. Okay, so let me just mention a few early stuff. These aren't quite pantograph equations, but the characteristic thing is that they've got a linear argument here. Q difference equations were big stuff in the 1920s and 30s, and they're still being studied now, but they just exploded. People like Markov and others looked at it. Why was it so important for what we're doing? Because it had to do with the linearization. I don't know how much people know about complex dynamics. I should have put that over there as well. Complex dynamics, you've got some holomorphic function. You have f of a holomorphic function, and if it's not, if it's this sort of a form, that is its first derivative. It's got a fixed point at z, and you've got a whole. It's probably easier to read this one. If it starts out like this, and then other garbage, let's say 0 is a fixed point, you can linearize, not linearize in the applied math sense, you can find a transformation that will transform this to that. So if I have a functional equation of some sort equals, let's say, some y of f of z, Koenig's linearization tells me it's a local thing, but near that fixed point, I can actually work with that instead. I can do that transformation. Of course, it's almost impossible to find the transformation, but in principle, it's there. And the reason I bring that up in here is because that means that pantograph type arguments aren't a real special thing. In fact, you can solve maybe a lot of other functional equations if you understand a bit about the pantograph equation. So I bring that one up. That's an old result, incidentally, 18-something, I don't know. Schroeder, very famous equation, pops up quite a bit. Poincaré, these are basically the same thing. Poincaré looked at it. So we're in the company of some big giants with this. Now what I want to talk about, first I'll just mention briefly theta functions. Now Graham's going to look at that and say that has nothing to do with the pantograph equation. There's not even a derivative there. And q is less than 1, and I've got these strange conditions here. This is done by a mathematician named Starcher, 1931. What does it have to do with the pantograph equation? Well, think laterally. If you go into a Laplace space, this is the Laplace equation of a pantograph equation. That's what it is. So it's related to a Laplace-type transform. Anyway, I just wanted to point out that a very classic piece of mathematics was done with this. I don't know, has anybody here ever thought about theta functions? There are like 4 of them, and they've got thousands of identities, and you have to go to Abramowitz and Stengen to keep your head straight what's going on. They're complicated, and the identities you get are complicated to prove, at least they were. But he went through this simple equation, here, and solved it by this. Okay, it wasn't a unique solution, but he put these conditions on, developed a Laurent expansion. You'll recognize that constant, Graham. It pops up in cell growth as well. And bingo, you get the third theta function. Now he took that and one other related equation that's slightly more complicated than that, and he developed the identities that took pages and pages and pages to get for theta functions. He did it in a 5-page paper. Okay, just by looking at it as a functional equation. Okay, so that's early relative. Now the next one, I don't want to scare people in an industrial maths, but the next one had to do with the partition problem. This is in number theory. Okay, that's a generating function for partitions. And the problem is, you're looking for this coefficient is the number of ways you can solve this equation where the k's are positive integers. I don't know, how many people are into partitions? Okay, well this is sort of Rogers, Ramanujan, that sort of stuff. Mahler showed that if you associate the coefficients with a function, it's sort of a step function from integer to integer, you get this functional equation. Okay, it looks nothing like the pantograph equation, except it has this linear scaling. N here's just some fixed number. And you come out with this in general. You study this general equation. And this is where I've read a lot of papers now on pantograph. They always say, oh, blah, blah, blah. Mahler did this, but he studied a discrete version and not the pantograph equation. And I say, oh, that's bollocks. if you actually read Mahler's paper, he did go to the Pantograph equation. Nobody gets past the first 2 pages of that paper these days, unless you're a number theorist, but you patiently go past that. You find that, in fact, he studies this equation, which was Graham's prize equation. Sorry, Graham, I already had it in my notes.
Sure, that's right.
Okay, and Graham brings this sort of equation up from cell growth and everything else, but here I've suddenly presented it as it arrives very naturally as a pure mass problem in partition theory. And here our old friend, theta functions. The whole theory is pregnant with theta functions. Okay, so we get a theta function here. I'm not going into any detail here, but what happens is Mahler looked at this. The limiting case is w goes to 0, that's where the derivative comes from, right? Mahler looked at this and said, okay, that's my set of solutions, and he put some more conditions on it, technical things. And what was a brilliant thing that he did is he showed by solving this Pantograph type equation that this family of solutions to the real partition problem here were asymptotic to that. Now remember, the thing back in 1940s and stuff, this is when, you know, Hardy, Ramanujan, and all that sort of stuff is going on. They were seriously interested in the asymptotic behavior, number of solutions as the integer goes to infinity. And so Mahler, a lot of clever analysis, finally came down to this. This lovely little relationship for the asymptotics of partitions. It all stems from the simplest Pantograph equation. And it thoroughly nails, when you were talking, Graham, about the role of this sort of an equation, it has absolutely a precise number theoretic application. It's an asymptotic first order approximation to the number of partitions. So, anyway, that's a paper. I think you guys remember Mark Twain. He defined a classic as something everyone talks about and nobody reads. That was Mark Twain's definition of a classic. I got a feeling, at least amongst the applied maths and differential equations people, they referred to Mahler, but they never read Mahler. And I found that he had a brilliant insight, and his asymptotics were pretty adventurous to go through, but kind of rewarding. Okay? Okay, well, hang on, we're doing applied maths now, so let me just point out a few things. Graham alluded to this. Here's our simple equation, and it's an initial value problem, let's say. And if alpha, let's say alpha is real, between 0 and 1, for example, it's easy to show. Just plug in a power series. And remember, alpha is less than 1, so these terms are going to go to 0 as n goes to infinity. It's easy to show that you get a nice solution. It's analytic at the origin. It's an entire function. You can do all sorts of order theory stuff on it and so on from complex analysis. But the point is, it's nice. It's a decent God-fearing thing. Right? Now, suppose it's an advanced case. What's the difference? Well, same problem, but now alpha is greater than 1. You get an infinite number of solutions. Okay, there's no uniqueness whatsoever. No solution, however, is holomorphic at the origin. You lose that. And if you require the solution to decay faster than 1 over x, it's going to decay exponentially. So the uniqueness then kind of goes built into an asymptotic condition at infinity, is what's happening here. Now this is what Bryce McLeod worked on with Cato, and wrote a big seminal paper about all sorts of variations, different signs, and so on for B and lambda. But that's the nub of it there. There's a huge difference just changing it from retarded to advanced.
How come it is unique in the retarded case? Because it has the trivial solution too. No?
Oh yeah, actually that should be y0. That was spotted, kill plot. That should be y0. It is unique to that. That only has one solution, and that's there's a constant out there that should be 0. But yeah, sorry about that. Yeah. Y is it's non-zero constant. Sorry. This is what a typical advanced solution looks like. Now I wrote Q as this because this is a partition function, straight out of number theory as well. This, however, I left it there to convince you that these are exponential arguments. They're screaming to 0 as n goes to infinity. This is an example of a Dirichlet series. It's holomorphic in the half plane, not at the origin. In fact, the imaginary axis, this is really interesting, something that I think I wrote a paper with you, Graham, and later on Hong O and I came across this, and we wrote a paper about it with nonlinear arguments, is that the natural boundary is the imaginary axis. It's a natural boundary you can't holomorphically continue across. So real z greater than 0 solutions don't talk to real z less than 0. Although there are solutions in both half planes, there's a natural boundary dividing them. And so that just gives you an idea of the richness of this equation, that it has these surprises that come up. And not only that, it's not your normal natural boundary that you get in, I think it would be second year calculus here. You know, where you have like sum of z at the n factorial. You show that's a natural boundary because it blows up on the circle. This is bounded and finite everywhere on the imaginary axis, but nowhere analytic. So it's quite an interesting creature in its own right. Now, in applications, and then get back, because I guess we are in applied maths here, aren't we? Back to applications, this light absorption problem in the Milky Way, this ruin problem in gambling, and the cell growth problem are a little bit different than some of the other things that have been studied, because they always require that the solution to that Pantograph equation be a probability density function. It has a definite statistical role. And indeed, the solution is still of this form here, but you have to normalize it. And you can kind of repackage it a bit. These a's are those complicated coefficients here. And you get solutions. This is k is a normalizing constant, same thing that appeared in the theta functions. These are sort of various Poisson distributions. And you get it as a sum of Poisson distributions. Now, when I was looking at it this way, I said, why is that? Why are we always getting that? Because I didn't understand any statistics, I still don't, but I have a wild guess at it. And that is because the Pantograph equation, and another thing that Graham and I and Gregory Durfel worked on, we really sort of unraveled that in fact it's any first order Markov sort of process produces these sort of Pantograph, or the certain class of Markov process produce Pantograph equations. And so that's why it appears in gambling. That's why it appears in all these probability things, because it is a very simple, just first order Markov. So we get these kind of results that come through. Okay, so that's the first order one. And what are some features? Well, it turns out I'd never have to say, even though I want it to be a probability density function, I never have to impose that. It always happens. And there's a deep reason for that. This goes back to its interface with ODEs and FDEs, that it's like a singular Sturm-Liouville problem, and the probability density function solution corresponds to the first eigenvalue, so there are no zeros. Okay, that was another unexpected thing. I mean, how many first order eigenvalue problems have you ever worked on? You always work on second order ones. But this is a first order one, and it has that behavior, just like a second order singular Sturm-Liouville. The solution is unique. Okay, by requiring it to be a PDF, that non-uniqueness is gone now. It's completely unique. We do not have to specify any more than it be a PDF, probability density function. It doesn't have to be 0 at 0 or anything like that, but it has to be integrable and differentiable. And the other thing is that that distribution always has to be unimodal, one mode, one bump. Okay, and that's something that didn't come till quite late. I think Graham's cell growth model was originally was in the 80s, and it wasn't until McLeod and DaCosta, well, that's the first time in print anyway, that they actually proved it was unimodal. So that is the first order case. Now let's take this for a real test drive. This is some stuff, some more stuff, a lot of it which I was thinking about at KAIST. The second order case. Now I'm going to raise the stakes dramatically here. We're looking at a differential equation like this. Here's this, what is called this non-local, this Pantograph type argument. D is a dispersion. G, in the cell growth model, G is a growth rate, and B is what? A splitting rate, right, Jeremy?
Splitting rate.
And this lambda here is an eigenvalue that will appear, and I'll show you in a minute where that comes from. But it's a traditional sort of an eigenvalue. A lot of people have worked on this. I just put a few down here. This was actually one of my first Korean connections. She was a Korean PhD student of mine. I had to do some work on this. Where does it come from? Cell growth. Graham actually talked about this in 2003, and I don't tax you to have a memory back then, but I'll just go through it very briefly. This is a Fokker-Planck equation that's modeling the number of cells, n, as a function of x spatial coordinate time t. Now, the size of a cell here is measured by its DNA content. So here's the definition of all of these. Here, alpha definitely is greater than 1. It's modeling cell splitting, not a fusion process. So a cell is split into alpha daughter cells under this model, and alpha is going to be greater than 1. So it's not a fusion. Now, to get back to the pantograph type stuff, when looking at the plant, and I forgot what the other one was, Graham, but they came out with solution curves that suggested separable solutions, SSDs. This was data that was brought to Massey as a problem. And so the original cell growth model looked at these sort of solutions, separable solutions, first thing you learn in PEEs. And what's really fun here is the fact that you can actually do it with this one too. You can separate the variables, and you get an eigenvalue out. Here mu is, I should have said mu is the mortality. We're going to lose that pretty quickly. Okay, so you get your time dependence here, and then you get this functional differential equation and the eigenvalue. Now the eigenvalue is important here. They don't really always important, but this one makes it interesting as well because it's not that easy to get, and it actually depends on the integral of the solution. So it's not something you can rattle off like some of the Sturm-Liouville. Okay, I'm looking for a probability function here, so these conditions come in. I actually need this condition too. I want to make sure that it's integrable with the splitting rate. But look at what the eigenvalue comes out. Okay, in order to know the eigenvalue, I kind of have to know what the solution is, or I can turn it into an integro functional differential equation or something like that, which is not an attractive thing to do. But still, it's an interesting problem because of this eigenvalue, and we've done some work on this, treating it like a singular Sturm-Liouville problem. You can prove that there is an eigenvalue. That was what David and I think Ronald did with that Klein-Rutman type theory. It was actually done earlier by McLeod as well, for the first order case. So we're guaranteed that there is an eigenvalue. Now, what I want to look at today is, in the literature, there's only been 2 published solutions. One of them has been constant coefficients that we did over Christmas a long time ago. And it didn't really come straight from the Fokker-Planck equation, but it fit in later on. Another one, we looked at the modeling of plankton's cell growth, and for these sort of coefficients here, there are either constants or generalized functions. Now that's kind of cheating because that means it's easy to get the eigenvalue and so on. But yeah, here I'm going to look at the case where I've got a quadratic dispersion term, a linear growth, and the splitting term's also quadratic. And what I've got down here is this is what the eigenvalue is, but of course I don't know that unless I know what y is. Now, without getting overly technical here, we put some growth conditions on there. So it has to decay a certain way at infinity and a certain way at the origin. They're kind of light conditions. And what happens? I can find the eigenvalue explicitly. Remember, the growth function is g times x. So if I put those in there and run through that, I can actually find that. That's one of these very rare cases where I don't need to know the solution to find the eigenvalue, and it's an easy kind of a number to keep too. And that's simply just simply multiplying through it and looking at the first moment, realizing that if it's a probability density function, that can't be 0, so this has to be 0. It's as simple as that. So it's a nice way to get around that problem. Now, what happens after this? Well, we got some qualitative results in here, and there are other classes of solutions that we've looked at, and these all follow a similar pattern. That firstly, it's positive. I don't have to impose that condition. any solution that satisfied those conditions before has to be positive. That lambda equals g is the first eigenvalue. There are other eigenvalues too, but that's the first one, and that instantly makes this positive. And the next one is it's also unique. Okay, remember that this is an equation notorious for being non-unique, having non-unique solutions. And we've just put a bunch of garbage in there with non-constant coefficients and so on. It's still unique. In fact, you can show it's unimodal as well. How do we solve it? Now, this is what is, I don't know what to call it, kind of funky way of doing it. Use the Mellin transform. How many people here have ever used the Mellin transform? 2. Okay. It's one of those things we teach and sometimes at university, but we never actually use in research. But when you think about it, the Mellin transform is one of the most natural transforms. It's more natural in a lot of ways than the Laplace transform with statistics because it's measuring the expectation, the moments of a distribution. It's exactly that. And so in these applications, especially with these sort of equations, where you've got x to some power times derivative, the Mellin transform is perfect. And nobody had thought to try this one. And I pestered Hong and I pestered Gangok and others about this, well, various visits here at KAIST, about maybe there's some way we can use that Mellin transform to solve things. And in fact, it works. It works just fine. That's our Mellin transform to remind people what a Mellin transform is. The conditions, the growth conditions that I use to get uniqueness and all that, so far all I've shown is if a solution exists, it's unique. And if a solution exists, it's positive. I haven't shown one existed. But under those conditions, I know I've got a Mellin transform in that strip. And if I put it in, the transform problem is this. That's just simply saying the integral is 1. That's just probability density function. And here's the new, well, it's all new, but this is a new bit here. This type of factorization. I write the Mellin transform as a product of 2 Mellin transforms. Now, why would anyone do that? There's a couple, I mean, I did it because it worked. But then when you think about it and come up with a more clever reason at a conference, you'd say, because the Mellin convolution represents the product of random variables. And that's exactly what's going on here. But I've got to be honest with you, I put it in here because it worked. It had a good feature about it. F here, if I had no functional argument, go back to this guy, if that were 0, this would just be a standard Bessel equation. Okay? What I do is I design F to be a solution to Bessel's equation. Just the straight equation. No functional bit at all in it. And Q takes all the heat. All the functionality of it, all the alpha influence is buried in that Q. So this is just what you get if you did the Mellin transform for Bessel's equation. Okay, so that's just that. That's just that. I already know what the solution is of that. So this is just keeping notation tame here. It gets fairly untame, actually. So I choose the modified Bessel function that vanishes, that decays at infinity. I don't want one that blows up because I'm going to write it as an infinite series of Bessel functions. So I choose this one and I say F is the Mellin transform of that solution. Okay? So I've carved this equation in 2 pieces, functional, non-functional bit. F is the non-functional bit, is simply the Bessel, the homogeneous solution, if you like. Q, if I put that into if I put it into this, Q has to satisfy this. That has a solution in terms of an infinite product. And the C is determined by this. This is just the fact that it has to be a probability density function. M of 1 is 1. It's like Y, the Laplace transform at 0 has to be 1. If one used that. And, okay, this is just me idly going away here, finding what C is. You can write C in terms of this sort of a relationship here. P is that, and if you really wanted to show off your theta functions and stuff, you can write it in terms of theta functions. That's not particularly interesting, but I bring that up because everything is tied in with these theta functions and partitions in number theory. Okay, and yet we're dealing with cell growth. Okay, that's my Mellin transform. Yum. That looks good. Gamma functions everywhere. You're thinking, oh my God, the thing has poles all over the place. What's going to happen? It turns out that all these poles cancel with the zeros of this product. Now, to give you a bit of history of how I discovered the eigenvalue was G, I wasn't clever enough to do what I showed you. What I did is I actually got this Mellin transform, and I was trying to eliminate all the poles. What value for the eigenvalue would get rid of the poles in the right half plane, and it turned out to be G. And I thought there's got to be a clever way to do that. And that's why I went back to that simple computation. But there are no, I mean, this has no poles in the past real z equals 1. But it can have a pole in the right half plane. We'll see that that makes a difference in what the solution form is. Okay, so this is just, it's holomorphic in this thing, so if G is larger than 1, then yeah. Anyway, how do you invert something like that? Okay, let me just back up. Like, here's the problem for the students. Go off and invert that Mellin transform. It's actually not too bad if you can write it as a series. Because the Mellin transform has this wonderful property that it transforms back to this. The alpha here, if that is y of x, then if the inverse transform is y of x, let's say, then this over alpha s is just y of alpha x. So it's got this beautiful, that's one of the most attractive properties of the Mellin transform for this type of analysis. It's if anything is built for Pantograph type equations, it's the Mellin transform because it has that property. So if I could pull this off, then I could invert it to get this type of series where this is just the homogeneous solution, that Bessel function, and I'm just scaling it up and up and up with A. It's just like that Dirichlet series, e to the alpha to the k x. Exactly the same thing going on. Okay, so what's P of k? Well, again, this is undergraduate, maybe maths, I don't know what they teach at KAIST, but this is Euler's identity. It's a partition function identity. And you choose, again, this is back with theta functions, but you choose your q's and z's sagaciously, and you get this relationship here, and again, you get these partition type coefficients coming in, you get this, which I haven't quite figured out what that's doing, but you can actually solve it. Okay? And this is the only time, I mean, there are only, like, I can only think of 2 other solutions out in the literature for any non-constant case, and the other 2 are fairly, generalized functions or something. So you get this series of Bessel functions. It's great. It's a kind of a generalized version of what they call a K distribution. I didn't know about this until I think I was ganging up and I was talking with him. When do you see a probability functions that are a series of Bessel functions? And he directed me to this, well, pretty much gave me information to Google on K distributions. And it appears that they use them all over the place in optics and other things. They use it in a different way. They have a bunch of spots and they want to tell you what distribution it is. But this is the first time I've seen one come up naturally through the analysis. Through the cell growth model here, suddenly we get K distributions, and that's quite interesting. So you see that this problem is feeding back into mathematics. It's not a stagnant, industry gets all the benefit. Okay, well, what's some other stuff? It's clear, if we want to look at the asymptotics of this, it's clear the Bessel function, like this modified Bessel function, decays exponentially. My solution is a series of these guys. And these coefficients P of k converge, they go to 0 very fast, so they're not causing any problems. Even this alpha to the k is swamped by that sort of a term. So it's going to decay exponentially. There's no, it's pretty clear it's an exponential decay, as we expect. It's the asymptotic behavior at 0 that's a bit more peculiar with this one, because I chose a Bessel function, a modified Bessel function k, because it decayed exponentially. And you can show, if I took the other one, I could show that I get a divergent series and so on. This one, however, does nasty stuff at the origin. Mu is just some fixed number here, but it's positive. generally, or it can be. So K does some nasty stuff at the origin. How's that going to work with our cell growth model? We need it to be integrable. It's a probability density function. All right, now this is where I really had to go back and think about classical mathematics. Because anyway, asymptotics with Mellin transforms. Great. The whole point is, and cut to the chase here, the whole point is that you can actually get a nice asymptotic relation by looking at the poles in the right half plane. First pole it bumps into, as you're going from positive infinity back, that dictates its asymptotic behavior as 0. Right? And so this is the sort of thing you can use to understand what's going on at the origin with these probability density functions. Okay, so it's just a piece of classical maths there. But it turns out there are 3 cases. And I wasn't expecting this at all. I was expecting a better behaved thing. This is something that doesn't happen at all in the first order. In the first case, it goes to 0. If I've got a fast g is growth rate, it's a linear growth rate g times x, but if that constant g is greater than 1, they all have to be positive here, if it's greater than 1, then my probability distribution function goes to 0 at 0. And that was the sort of boundary condition that Graham and I were working on for quite a while, trying to get y to be 0 at 0. If it's slow, however, it actually blows up. It goes to infinity. But it's still a PDF. Why? Because the exponent there, it's 1 over x to something less than 1. So the neutral case is quite a fun one because it goes to a constant. If g is equal to 1, things cancel out. It doesn't blow up, but it doesn't go to 0. It goes to this number here. And R of A is that. Again, another partition function. And okay, here I was just dragging you back through theta functions again, but that's that in terms of theta functions, that's what R is. So the whole thing is full of these partition problems. And let's see, finally here, oh yeah, it's quite easy to show the derivatives, have a similar type behavior. So the growth coefficient, that g is a crucial parameter in there, more so than it seems anything else about what the shape is with these type of functions. And this, well, in the conclusion on that particular example is that you can get that. I've already got uniqueness separately, so all I had to do was construct a solution, show that it's a solution. I already know it's unique. I already know it's positive. Okay? So that's why I went that backwards way to get uniqueness first, because I knew I was on safe ground. If I could pull this off, then I knew I had the solution. And it turns out you can get it very elegantly with this Mellin transform approach, but it then adds other questions to it. And this is one for the audience. This thing is absolutely, as I've said, absolutely pregnant with number theory and partition theory. It's telling us something about how cells are partitioned, particularly in their initial distribution, how this model is partitioning cells, and it's partitioning them according to their history. If you're a cell of this size, how did you get there? You either grew to that size or you split down to that size. How many different ways can that happen? And I have not actually explored this far enough, but I believe that's where the partition end comes in. It's telling us how those cases are. And this is some place where we can take this. It's taught us a bit about statistics and some things, and it's actually given us some other uses for the Mellin transform, but how now it can be used to turn it around and feed it back into the cell growth problem, and we can at least understand in our model what implicitly we're asking the cells to do in this type of partition. So I'll leave it at that. I'll stop there.